All right, welcome back. Today we're gonna talk about surface energy and surface tension. Okay. You use gamma sign for both of them. So in terms of surface, it's a kind of defect. Okay. So there are zero-dimensional defect, one-dimensional, two-dimensional, right? And this we already learned that it's point defect. Okay, it includes something like Schottky Wagner defect or Frankel defect, or defect in elemental crystal, right? And one dimensional is just a one dimensional collection of defect, which is this location. And two dimensional is the topic of today, that is surface or interface, right? And interface. So surface is just what it is. It's just the surface of this material. These are all surface, right? And interface is can be many things. So let's talk about interface first. There are many different interface like solid vapor, solid liquid, or even solid solid. And uh, story short, um, gamma SV is highest in energy, then and gamma SL, and then it's gamma SS. Why? It's because the difference in surface energy between different phases, and solid and vapor has the most difference, so their interface is very unstable. Okay, so interface energy is going to be the highest for solid and vapor. And there are many like different, even there are liquid interface, like if there are two immiscible liquid, this is maybe some kind of oil and this is water, then they are not going to mix, or because due to difference uh, in density, and they are immiscible, then we can also see this kind of boundary, right? And these are all liquid interface. And what is solid solid interface? It is grain boundary, which is very crucial for material scientists. The definition of grain boundary, sorry, is um, interface caused by um, not homogeneous phases. Caused, no. Interface between different phases. Let's just say interface between grains. That is simpler. So grain inside the grain, homogeneous phase. Meaning inside grain, homogeneous phase. Homogeneous mean same physical and chemically, physically and chemically, it's the same inside this grain. Like this kind of grains, grain A, grain B, it can be like completely different materials. Like this is alpha phase, this is beta phase, with different crystal structure. Like here it's BCC, here is FCC. This kind of structure or it can be something like alpha 1 and alpha 2, which is same structure like FCC. When you look at some kind of eutectic diagram, then here it can be either alpha plus beta or alpha plus alpha 1, right? And in this kind of graph, you'll see lots of this kind of grain boundary because alpha and beta coexist in these phases, okay? So between these grains, you'll see grain boundaries. These are all grain boundaries. And today we will talk about surface energy and tension, right? And we will first derive what these are. So let's say there is this kind of rod here. So this thing is a three-dimensional structure. It actually looks like this. And the rod is here. And these and here too, right? These two surfaces. And now you're gonna pull or even push this rod, and these two surfaces are going to reduce, okay? And the force needed to expand these surface is surface tension. Now, when you think of water, there are surface tension. The water is going to look like this. This structure is because it wants to shrink. It wants to minimize the surface area, right? Oh, we will first, let's forget about this model for a second. Let's first talk about what is surface energy. So you remember this U equals TdS minus PdV, right? du, first law. And here, this minus PdV is the reversible work. That's how we concluded in thermodynamics 1. And here we only focused on mechanical work before. But now we are going to include all different work. Work is work caused by some kind of different force, right? And it can be many things, gamma dA, or many other different work, like let's say FDL, right? Or QDV, right? Many different work. And we are only going to talk, so you can choose different model based on your need, based on the problem. When you're dealing with electrochemistry, then you can choose this. When you're dealing with surface energy, like in this case, we can choose this. So we can rewrite the first law, which will become du equals TdS minus PdV plus gamma dA. And dg will become ST minus STT plus VdP plus gamma dA. How? You can easily derive this because G is H minus Ts equals U plus PV minus Ts, and dg is d, so you combine these part will be, let's just dh minus tds plus minus sdt and equals du plus vdp minus tds sdt, and here we plug in here, right? And so tds minus pdv plus pdv plus vdp minus tds minus sdt plus gamma dA, right? And this will go. This is also going to go. We have these three remaining. So dg becomes sdt plus vdp plus gamma dA. All right. So this is our formula for Gibbs-free energy change, infinitesimal Gibbs-free energy change as temperature changes or pressure changes or area changes, right? So you can say, we learned this before, that G, Gibbs-free energy, is a function of temperature, pressure, and area. In this particular model where we only consider mechanical work and surface energy work, all right? Then you can get this dg round G, round T will become minus S, P a constant, round G, round V, round P at constant temperature and area is volume. Round G over round A at constant temperature and pressure is Gibbs-free energy. Okay, here is not Gibbs-free energy, it's surface energy. All right, and because we want to minimize dg, right? We want to minimize dg in order to make this this kind of any kind of your system into equilibrium. You want to minimize dg, you have to make it constant. So that's why gamma will also try to like decrease, right? So the material dg equals minus sdt plus vdp plus gamma dA. So at constant temperature and pressure, this material is trying to minimize dg by minimizing this term. And gamma is an intrinsic property. It doesn't really change. It depends on the material. It's an intrinsic property of this material. It's not going to change because of the shape of the material or anything else. This at constant temperature and pressure, there is a constant value of gamma. Okay, whether if it's a star shaped or a sphere shaped or a square shaped, it is going to be same gamma at constant TP because we just derived. All right. del G del A TP round G round A is equal to gamma. All right, so we want to minimize area in order to decrease Gibbs free energy and make it equilibrium. Sorry. Decrease Gibbs free energy. All right. Then we can finally get our definition for surface energy. There are two different kinds of definition. First, it is energy needed to expand the unit area. Okay, so you can use like this, W delta A. Or you can also think of it as summation of excess energy on the surface. But this definition, we are going to talk about it in next lecture, so you can just forget about it for a second. So this is our surface energy, and it is a constant term regardless of shape. It depends on the material, it depends on the crystal structure, it depends on the intermolecular force. Yeah, it depends on all those. Oh, it's crystal structure, or what kind of bonding, like whether it's ionic or metal or covalent bond. It depends on those things. It doesn't depend on the shape, okay? Regardless of shape. This is the surface energy definition. Now we are going to talk about surface tension. Now we can finally get back to the model we used here. Okay. Okay. So we want to the system is going to try to minimize Gibbs free energy by minimizing the surface, which is why when you see rain dropping, you'll see this kind of shape, right? Like this. It is simply because this is because it wants to minimize surface area. Sphere is model that can minimize the surface area at constant volume. All right, so this is why they choose to be sphere. Okay, sorry. And back to this model. So the system want to minimize the surface area. So you're going to have to use certain amount of force to pull this rod, right? Because the surface is going to hold it like this. These two surfaces. Remember, there are two surfaces. We talked about it. This is a top view. And when we look at it like this, two surface is gonna hold this rod. So you want to pull this rod like this. Think of this as a liquid, okay? Don't think about it as a solid first. It's a very sticky, let's think of it as a sticky liquid, okay? Then you'll need some kind of force to pull this like this. Then you can come up with a formula. How much force are you going to need to how much force is needed to pull, right? Which is F equals so F times F is going to okay, so the force needed to maintain or expand this to surface is going to equal to surface tension times, so let's think of it, the unit of this is Newton per meter. Okay, so that is the force in this surface per the length here is L. Okay, then it's F divided by L. 2L is going to equal to surface tension. So force needed is gamma times 2L, because gamma is Newton per meter, right? So per meter of here, this is L. Let me use this. There will be a certain amount of force here in per unit meter, like this. It wants to shrink. There is this kind of force making the liquid shrink and make the area minimized. So there is this kind of force, and the unit is Newton per meter for surface tension. And you have two surface, that's why there's a 2 here. Two surface producing that kind of force per meter, so you have to times L. So this amount of force will be here, like this, holding this rod backward. And then if you want to make this rod move or stay maintaining this position by force equilibrium you learned from general physics, you need this kind of formula, right? Then this is the definition of surface tension. So the amount of force needed to pull the rod. That is the definition of surface tension for liquid case, okay? And if you get back to how it connects with the surface energy, in liquid cases, surface tension is same as surface energy. They are same concept. It's really same. I'll show you why. Surface energy is this. We just derived that gamma equals dg over dA, right? At constant temperature and pressure. So it's basically the same notation because infinitesimal, if you change this, and this already has a delta meaning, I told you. So if you make this infinitesimal, then at constant temperature and pressure, del G equals this reversible work. So this becomes reversible. So gamma is work A, right? So this is surface energy. The work needed to change this amount of area, okay? Then we can just write like this. equals the same surface tension definition is like this. You'll see they both have the same unit. Joule per meter squared and Newton per meter is basically the same unit. You'll realize because Joule is Newton meter. Okay, so which is equal to gamma. They are same when it comes to surface liquid. It's different. This is very important. Surface tension and surface energy are same for liquid, not for solid. All right. Then, yes, we concluded that. This is the conclusion. Okay. Good. You'll see that the force needed to hold this rod here like this. Okay, let's do this first. So I'll show you how they are the same. So delta A equals 2L delta X in this model, right? You take this. If this is delta X, then this is delta A divided by 2 because there's two surfaces like here. So delta A equals 2L delta X. Then this is the amount of change in energy, a change in area, and your force is going to do work equals to force times delta X. Then work over change in area, which is the definition for surface energy, is going to equal to F times delta X over L 2L delta X is F over 2L, which is surface tension. See? So we just proved that this is same for liquid. But this is different for solid. We'll keep talking about that in next lecture. But this is the basic introduction to surface energy and tension concept in liquid. So much for our lecture today. Thank you for listening.